Hello children and welcome to my channel Chemistry by Miss Nidhi Banga. Today we will be talking about competency based questions from all of the organic. These are asked for generally 3 to 5 marks and they're almost always asked. They're very commonly seen in board exam papers. Okay, so before getting started, uh, let's make sure that you know your stuff. You should have your name reactions. Either you prepare them really nicely or have them written on a page so that you can refer to them when need be. Your special reagents like your sodium borohydride, lithium aluminium hydride, Debye and tolerance reagent, valence reagent. These also express that you have them written down on a page so that you can refer to them. Common chemical properties. If you have read your chapters nicely, then you're already aware of the common chemical properties of the organic compounds that we have in our syllabus. For example, your carbonyl compounds, they react with ammonia derivatives, right? 2,4-DNP, for example. So these kind of common chemical properties you should be aware about. Apart from that, what also really helps is knowing your chemical formulas. So if your chemical formula is CnH2n plus 2O, just one O, and number of hydrogens are 2 more than twice the number of carbon, in that case, it can be your alcohol or ether. But if the number of hydrogen is only twice the number of carbon and one oxygen is there, then that can be your aldehyde or ketone. Okay, these two are functional groups. So are these two functional group isomers. Okay, so these two are functional group isomers and these two are also functional group isomers, right? But if you have two oxygens, then that gives you the hint that it can be a carboxylic acid. Okay, pay attention at the number of carbon and hydrogen, right? It can also be an ester because carboxylic acid and ester are functional group isomers. But all this is true for aliphatic compounds. Okay, it doesn't hold, this thing doesn't hold when your compound is an aromatic one. How do you know if your compound is aromatic or if it has a benzene ring? So if your number of carbon atoms are more than 6 and number of carbon atoms and hydrogen atoms are more or less equal, then that gives you a very strong clue that it has a benzene ring involved. Okay, if you are clear about that, we can start. So to save your time, I have drawn the outline for most questions. So first question, X with molecular formula C5H10O. That means CnH2nO. So it's your aldehyde or ketone. We also know this because it gives a positive 2,4-DNP test. Carbonyl compounds such as ketone and aldehyde, they give positive 2,4-DNP test, right? But it gives a negative tolerance test. Out of aldehyde and ketone, which gives positive test for tolerance? Aldehyde. So if it gives a negative tolerance test, that means it's a ketone, right? On oxidation, it gives carboxylic acid Y with a molecular formula C3H6O2. Now this is also another clue that the compound here is a ketone. Why? Because upon oxidation, its number of carbon atoms is decreasing, right? That happens if it's a ketone, because in case of oxidation of ketones, the carbon-carbon bonds break. Okay. Potassium salt of Y undergoes Kolbe's reaction and gives a hydrocarbon Z. Okay. So let's talk about this. C5H10O, your ketone upon oxidation gives you this compound. This is a carboxylic acid and it's a 3-carbon carboxylic acid. So what are your options here? This is your only option. Since carboxylic acid is a terminal functional group, this is the only carboxylic acid which is possible with 3 carbons. Okay, so if this is the carboxylic acid, think about this again. This tells you that your ketone group, the carbonyl group, is present on the 3rd carbon, right? That is why upon oxidation, either this bond breaks. If this bond breaks, then this is your carboxylic acid. And if this bond breaks, then also this is your carboxylic acid. What was the other option? If it's the carbonyl group is not on the 3rd carbon, we could have it on the 2nd carbon. But would that satisfy this condition? If it was on the second carbon, then upon oxidation, if this bond breaks, you would get only 2 carbon carboxylic acid. And if this bond would break, then you would get 4 carbon carboxylic acid. So this cannot be our ketone. Our ketone can only be this. Okay. Anyway, there were only these two options with 5 number of carbon. Carbonyl carbon present only on either on the second carbon or on the third carbon. Okay. And this one is ruled out because we know that the compound that we get upon oxidation is a 3 carbon carboxylic acid, which is only possible if our ketone is this. Okay. Now, potassium salt of Y. This is our Y. So potassium salt of Y, that is your CH3CH2COOK, undergoes Kolbe's reaction and gives a hydrocarbon Z. Now this is not the Kolbe's reaction that is there in grade 12, that is the formation of salicylic acid. This Kolbe's reaction is the one from your grade 11, Kolbe's electrolysis. So what happens in that is that this is your potassium salt of carboxylic acid. This electron here comes here. The electron from this bond comes here, single electron, because this is push hook arrow, and another electron, the other electron comes here. So what you get is a radical, ethyl radical you would get. And since it's a radical, it would very quickly combine with the other radical to give you your hydrocarbon. So this is the hydrocarbon Z that you get upon Kolbe's reaction. So your X is this, your Y is this, and your Z is this hydrocarbon, butane. All right, let's move on to the next question. But before we do that, let's very quickly go through ozonolysis, because that would be used in many questions, at least 2 questions that I'm taking today. So ozonolysis is a method of preparation of aldehyde or ketone from alkene. The reagent that we use is ozone, of course, and then it is followed by zinc dust, addition of zinc dust, and then hydrolysis. Okay, so this is the reagent that we use. Let's see how it happens. Let's say this is the alkene that we took. It's an asymmetrical alkene. Okay, now when we add ozone, ozonoid would be formed. And how would you make that? Just make a temple or a hut-like structure here, okay, in place of double bond. So this is your ozonoid. Okay, then when you add zinc dust into it, what happens is this goes here, these electrons go here, these electrons go here, and these electrons go here. Okay, and what you get is this compound, then this you get, and then this oxygen that is left combines with zinc and ZNO is formed, which is removed. Okay, but if you don't have time for this, if you just want to know the products that would be formed upon ozonolysis, there is a very simple method. What you do is, the double bond that you have, you break that double bond into 2 double bonds and put oxygen on both sides. So what you will get is this carbonyl compound and then this carbonyl compound. These two you will get if you just break the double bond into 2 double bonds and put oxygen on both sides, right? So now see, because this side of the double bond we had an H, so this would give us an aldehyde, and since on this side of the double bond we had only carbon, so that would give us a ketone, right? So your products would really depend upon the structure of alkene. Okay, so now if the other thing is that if you have a symmetrical alkene, and you break the double bond, put both sides, then what you would get? You would get only one single product, because on the both side of double bond you had the same groups, right? So you will get a single product if your alkene is symmetrical. So if in the question the hint is given that only one aldehyde or ketone is produced, then your alkene was symmetrical alkene, right? Then at times you would also have to write the alkene from which the two products are formed. So let's say we have propanol and propanol. These two products we have, and we want to know the alkene from which they were formed upon ozonolysis. All you have to do is write them in such a way that their carbonyl carbons oxygen are facing each other. And then you just remove the oxygens and join them through double bond, of course. And here is your alkene, your starting alkene, right? So ozonolysis is very simple and it's very commonly asked. So let's see some questions which have ozonolysis. Okay, so your ketone A, C4H8O, even if it was not given ketone, you would have guessed from the formula that it's either an aldehyde or ketone, which undergoes a haloform reaction. So this gives you clue about the structure of ketone. So this means that this ketone, this 4-carbon ketone, also has this group. Then what are the other options? On the other side, you can have only this. Okay, there is no other option. So we have figured out the formula of our ketone. Okay, now this ketone upon production gives a compound B. So aldehydes and ketones upon production, they give alcohols. Since it's a ketone, it would give a secondary alcohol. So this is a secondary alcohol. In the next step, it undergoes dehydration because of sulfuric acid. So for your convenience, I have written it in this manner. So this is your alcohol, secondary alcohol, which was formed upon reduction of the ketone. Now, upon dehydration, when you treat it with concentrated sulfuric acid, what will be formed? Which alkene would be formed? There are two possibilities. One is that OH from this and the hydrogen from this first carbon goes. Okay, in that case, you will get a double bond here. Okay, the second option is this OH and this hydrogen leaves. In that case, you will have your double bond between these two carbons. Okay, second carbon, third carbon. Okay, so these are the two options and they will give these two alkenes. Both will be formed. Of course, major product would be this because our Seytsev rule says that most substituted alkene is formed. So this alkene is more substituted as compared to this alkene. So this would be our major product. And we also get this by the next clue. So this compound C, which could be either this or this, forms a monoozonide D. And D on hydrolysis with zinc dust gives only acetaldehyde E. So that means only one product. See, monoozonoid and hydrolysis with zinc dust, this gives you clue that we are talking about ozonolysis. Okay, so in ozonolysis, your final product is only one product, acetaldehyde. So that means your alkene has to be symmetrical, and this is the symmetrical alkene. Okay, so after we have ruled this one out, let's make the structure of D. CH3, CHO, CH, CH3, O, O. This is your ozonoid, which upon reaction with zinc dust, hydrolysis with zinc dust, gives only acetaldehyde. Okay, so this is your A, this alcohol is your B, your C would be this alkene, D is this ozonoid, and E is the acetaldehyde. Okay, I hope it makes sense. Let's move on to the next question. Again, this is an ozonolysis question. We have an alkene with formula C5H10, which on ozonolysis gives a mixture of two compounds, B and C. Since we are getting two compounds, we know that this alkene is not symmetrical. So let's see what are our options. If you have a 5-carbon alkene, you can have a double bond placed between first and second carbon, then third, fourth, fifth. Okay, or you can have it placed between second and third carbon. Okay, first, second, third, fourth, fifth. If you put it here, it would be same as this one. And then if you put it here, it would be same as this one. So these are really your only two options. Okay. So now upon ozonolysis and hydrolysis with zinc dust, it gives you two compounds. Okay. So one has to be, they can be anything. Let's see what they are. Compound B gives a positive Felling's test. If it gives a positive Felling's test, that means it's an aldehyde, because ketones do not give Felling's test or ketones or Tollens test. So this is your aldehyde, compound B, and it also reacts with iodine and NaOH. That means it gives a positive iodoform test. That means it has this group and an aldehyde, which solves the problem. This is our aldehyde, this is B, right? Now C gives a negative Felling's test, that means it's a ketone, and it gives a positive iodoform test, that means it also has methyl ketone group. Now our alkene was 5 carbon alkene, 2 carbon are taken care of, here also 2 more carbon are taken care of, then that means you can only put a CH3 here. Okay, so this is your C. Alright, so acetaldehyde is your B, acetone your C, and alkene would be then, let's see, CH3, COH, and CH3, CH3 here. Remove these two oxygens and you get this as your alkene. Okay, so this is your alkene. Okay, so now our next question is, an aromatic compound X with formula C8H8O gives a positive 2,4-DNP test. First off, it's an aromatic compound, which we also can figure out because carbon number is more than 6 and the number of hydrogen is almost same with that of carbon. 2,4-DNP test is positive, that means it has carbonyl group. It also gives a yellow precipitate with iodine and sodium hydroxide, which is a haloform reaction, the iodoform reaction. Alright, so this yellow PPT would be of CHI3 and then Z is formed. Okay, we'll figure out what this Z is in a while. It gives a negative Tollens test, that means it's a ketone. Upon oxidation under drastic condition, it gives this carboxylic compound, this carboxylic acid, C7H6O2. So with 7 carbon and 6 oxygen and 6 hydrogen and 2 oxygen, what are our options? This is our only option. C6H5 from the phenyl group, then 1 carbon, that means C7, and then 1 more hydrogen, that means H6, and 2 oxygens. So our benzoic acid fits this description, fits this formula. So if Z is benzoic acid, and since it gives iodoform reaction, so that means it also has this methyl ketone group. So that means our X has to be acetophenone. 6 carbon, 7 carbon, 8 carbon, 5 hydrogen and 3 hydrogens, so 8 hydrogens, and 1 oxygen. Okay, so this is acetophenone is our compound X. Y would be iodoform, Z would be benzoic acid. Okay, all right, let's move on to the next question. An organic compound A upon reaction with nitrous acid gives you B. Now nitrous acid reaction with nitrous acid gives us diazonium salt, but this is an aliphatic compound, so it's an aliphatic diazonium salt which is not stable. So if it's not stable, it quickly hydrolyzes to give us alcohols. So with only 2 carbon, what are our choice? This is our alcohol and this would be our primary amine. Okay, so this much we could figure out only by this statement. So what else do we know? Our B, that means our ethanol, combines with C, an organic compound, and gives us D and E. D is a carboxylic acid, E is an ester. So carboxylic acid has this group, ester has this group, right? O, R. So that means they both have the C double bond O groups in the product. In the reactant, in B at least, we don't have any carbonyl carbon. That means our C should be source of these carbonyl carbons, 2 carbonyl carbons. So which organic compound has 2 carbonyl carbons? Anhydrides. Our anhydrides have 2 carbonyl carbon. But which anhydride? This we get from this information. Our ethanol upon oxidation with acidified K2Cr2O7 gives us D. So your D would be obviously acetic acid. So this is your acetic acid. So your acid is acetic acid. So this anhydride has to be acetic anhydride. So in your ethanol, the lone pair on oxygen would attack this partially positive carbonyl carbon, and this electrons would move here. Okay, so this would give you acetic acid, this acetate ion, and then from here you would get an ester. So let's start with this. Let's start with this. CH3, C double bond O, then O, then CH2, and then CH3. So this is your ester, and this is your carboxylate ion, which upon hydrolysis would give you carboxylic acid. Okay, so this is your D, E, B would be your alcohol, and A is your ethylamine. Okay, let's move on to the next question. An organic compound A with molecular formula C5H8O2. Now C5H8O2, your first instinct would say that it's a carboxylic acid or an ester. But take a closer look at the number of hydrogens. It's not twice the number of carbon, which is the requirement for aliphatic carboxylic acid or ester. Okay, so this is not carboxylic acid even though it has 2 oxygens. Let's see what else is there. So this A compound combines with hydrazine in presence of NaOH and glycol and gives you N-pentane. So if it rings a bell, it's a hydrocarbon, and hydrocarbon are produced from carbonyl compound by Wolff-Kishner reaction. These reagent, they are Wolff-Kishner reactions reagent. Okay, so that means it has to have a carbonyl carbon, at least 2, because there are 2 oxygens, so it has to have 2 carbonyl carbons. But where are they placed? Let's see. This clue that it has 2 carbonyl carbon is also given by this reaction. With hydroxylamine, it gives a dioxine. Dioxine is only possible if there are 2 carbonyl carbons. Now, it gives positive iodoform test. That means it has methyl ketone group. It gives positive tolerance test. That means it also has an aldehyde group. So let's see what is our option. You have this at one end and you have this at the other end. Just fill in the gap by CH2s. Okay, so this is your A. All right. Now, if you were to write the reaction with iodoform and tolerance test, so with this A, iodoform reaction would give you yellow precipitate of iodoform. And then you see this part formed iodoform. So the rest of this part will get oxidized. So you will get, if I'm writing from here, this, then CH2, then CH2, and then C double bond O, O, Na. Okay, this is what you will get from iodoform reaction. Tolerance test. In tolerance test, we have this compound plus Ag2O. That means Ag in plus form, +1 oxidation state. So in that case, the aldehyde group will get oxidized and rest of it will remain the same. So you would get this, and silver from +1 oxidation state will get reduced to metallic silver. Okay, so this is your reactions with tolerance reagent and with iodoform. This one is your product with iodoform, this one and this one, and this one would be your product with tolerance reagent. Okay, so let's move on. An aromatic compound A, upon heating with bromine and KOH, forms a compound B with molecular formula C6H7N. So if you remember this reagent, this is Hofmann bromamide reaction. Bromamide, that means this has to have an amide, and this is also aromatic. And upon after going this reaction, undergoing Hofmann bromamide reaction, it's giving us this from the amide group. This is removed, so it's giving us primary amine, right? And of course, it has to be again aromatic, because only C double bond O is removed. So C6H7N, what is the possibility? C6H5, this benzene ring, then NH2. So 1 N and 2 hydrogens. So this structure fits this formula. So if this is your B, that means your A is this benzamide. This is your benzamide, this is your aniline, right? Now it's undergoing a reaction CHCl3 with alcoholic KOH. Now CHCl3 and KOH, you encounter this twice in your book. One is Remer-Tiemann reaction and the other one is carbylamine reaction. Now in carbylamine reaction, we use alcoholic KOH, and in Remer-Tiemann reaction, we use aqueous KOH. So this is clearly carbylamine reaction or isocyanide test. So this would result in formation of a foul smelling compound. Okay, and that would be the isocyanide of this. Okay, so this is your benzene isocyanide or phenyl isocyanide. Okay, that's it. Moving on with the next question. An aromatic compound, this is an aromatic compound, combines with CHCl3KOH. Like I said in the previous question, CHCl3KOH is used twice, Remer-Tiemann and carbylamine. Let's see which one is this. It gives us two products. Both of them, upon reaction with zinc dust, gives us only one product. Now, if you remember zinc dust, one zinc dust is used in ozonolysis, and then there is a very important reaction of zinc dust, that if we add zinc dust to phenol, we get benzene. This is a very important reaction, and ZNO. Okay, so if these two compounds, upon reaction with zinc dust, they are giving us only one compound. That means that the phenol group over the benzene is being removed and only one other product is remaining. One other substitution remains. So let's see what it means. This is our aromatic compound and it's giving us this. So that means this cannot be carbylamine reaction, because ultimately we are not getting nitrogen anywhere. Okay, so this has to be Remer-Tiemann reaction. Okay, so Riemann-Tiemann reaction means that our aromatic compound is phenol, because in Riemann-Tiemann reaction, phenol when reacts with CHCl3 and KOH, it gives us salicylaldehyde. Okay, and one para product is also formed. Okay, so ortho and para both are formed. This is salicylaldehyde and this is the para product. Upon reaction with zinc dust, they both will lose the OH group. So obviously you will get a monosubstituted product, which is your benzaldehyde. Benzaldehyde upon oxidation will obviously give you benzoic acid. Now benzoic acid upon reaction with soda lime gives you what? So benzoic acid, this soda lime is a special reagent that is meant for decarboxylation. Decarboxylation meaning removal of carbon dioxide. So if you remove carbon dioxide from it, you get only benzene. Right? So your D is benzene, which you also get if you treat A with zinc dust. Your A was phenol. So phenol, if you treat with zinc dust, you get benzene. So sorted. Let's move on to the next question and the final question. So here, 2 moles of organic compound A upon treatment with a strong base gives you 2 compounds B and C. Now, when an organic compound is treated with strong base, with base you have 2 reactions. One is your aldol condensation and the second one is your Cannizzaro. In aldol condensation, we have dilute base. Strong base means concentrated base. So that is one clue that this reaction can be Cannizzaro. The second clue is that, and the stronger clue is that, it's giving us 2 products. Okay, if it had been aldol condensation, 2 moles of the aldehyde or ketone with alpha hydrogen would have given us only 1 product. Since we are getting 2 products here, that means this is Cannizzaro reaction. Okay, so these two, one of them is reduced product and the other one is oxidized product of A. Now B, upon dehydrogenation with copper, that means with oxidation with copper, gives us A back. So if B upon oxidation is giving A, that means B is the reduced product. Okay, that means B is the alcohol, because Cannizzaro takes place with aldehydes without alpha hydrogens. Okay, so this is the alcohol, that means this is the carboxylic acid. Actually, salt of carboxylic acid. Which salt? Depends on the base. Usually we use concentrated KOH, so that would be potassium salt. Potassium salt of carboxylic acid. Upon hydrolysis gives us the carboxylic acid, which is CH2O2. That means it's your formic acid. If this is formic acid, that means the alcohol is methanol and that means the aldehyde is HCHO, which is also logical because Cannizzaro only takes place when there is no alpha hydrogen, and in formaldehyde there is no alpha hydrogen. Okay, so that's it for today. I hope this helps you. I hope you feel more confident about these kind of questions now. And if you liked this, if this helped you in any way, please like, share and subscribe. And thank you for watching.